This is lesson 7.6 of our calculus class. Unit 7 is called Applications of Integration. Lesson 6 is called Volume using triangular and circular cross sections. What we're going to do in this lesson is figure out how do we find the volume of a triangular and a circular object using integration. So how do we write that integral? So first we're going to make sure we understand what we're talking about as far as conceptualizing that shape. So if we take a region bound by two curves, f of x and g of x, and we say, okay, that is the base of some solid shape. But this solid shape is such that if we cut it straight up and down, the cross section is going to be an isosceles triangle, such that the base is one of the legs of the triangle. So on the back side, there's a height straight up and down of this triangle, and that height is equal to the width of the base of this triangle. So those are the height and the width are our two legs, and then this diagonal side would be the hypotenuse of any cross section. So if we wanted to calculate the volume of this shape, which is a very important question that you use every day in your life, we have to know, okay, first of all, the formula for the area of one of those cross sections. The formula for the area of a triangle is half of the base times the height. And so the base is just going to be top function minus bottom function, so f of x minus g of x. And the height, since this is an isosceles triangle, and one of the legs of the isosceles triangle is in the base, then the height is going to be equal to that base. So the height is also going to be f of x minus g of x. So the area for any isosceles triangle that would be a cross section of this solid shape would be 1/2 times the base times the height, or 1/2 times f of x minus g of x times f of x minus g of x, which we can simplify to be 1/2 times f of x minus g of x squared. And if we integrate this thing from a to b, as in a being the beginning intersection point, x value, and b being the endpoint, x value, we can integrate from a to b of that area function with respect to x, and we will get the volume. Now if I take this thing and I imagine that it just makes this kind of rounded top with a flat base, such that if I do a perpendicular or vertical cut of this, the cross section would just be a semicircle or half a circle. And the area for half a circle would be, well, the area for a circle would be pi r squared. So the area for half a circle would be pi times 1/2 of r squared. 1/2 meaning we're just doing half of the area, or the area of half of a circle. So if I calculate this thing from a to b, it would be integral from a to b of pi times the quantity 1/2 times f of x minus g of x squared, or 1/2 of the radius squared times pi. Notice that if we distribute this squared, 1/2 becomes 1/4, and pi times 1/4 are both constants, so both can be pulled out of the integral, leaving us with pi over 4 times the integral from a to b of f of x minus g of x squared with respect to x. All right, so some examples here. Okay, so this is a region that we found bound by our two equations, and it is the any cross section of this solid. Well, let's say here, okay, the solid we can't see, we just see the base. So the base, the shaded region is the base of a solid, such that a cross section of this solid would make an isosceles triangle, isosceles right triangle with a leg in the region. So that means the leg in the region is the width, and the leg going straight up is the height, and those are equal in length. So the top function minus bottom function is going to be the width and the height. And since it's the area of a triangle, we divide it by 2. And that's going to be our area equation. So then we integrate it from the beginning point. So a value is 0. And then we integrate it all the way to the end point where they intersect again. And this b value, how do we calculate that b value? Well, two ways we can do it. We want to find when f of x is equal to g of x. So we could take e to the power of x minus 1 and set it equal to 4x and solve for x. But if you know anything about e exponentials, this is actually kind of a complicated solve. So what we're going to do instead is you're going to go to graphing calculator. You're going to type in for y1, you're going to type in this function, e to the power of x minus 1. And then for y2, you're going to type in 4x. And then we can use our graphing calculator to graph those two functions. And we can press the calculate button. Right next to the graph button is the calculate button. And we can select the intersect option. We can pick our lower curve or upper curve and guess where the intersection is. And our calculator will tell us the intersection point. The x value of the intersection point is what we're looking for. So if you do that correctly, you should get x value of 2.337 or something that rounds to that. That'll be our upper bound for this problem. All right, so we take this shape and we say this shape is the base of some solid object that's got this top rounded edge, and that we take any cross section and then we would get a half circle or a semicircle as a cross section. The volume of this thing would be integrating the area function for this semicircle. The radius of this semicircle would be top function minus bottom function. Yeah, and then we'll go from there. We'll put that in, so pi times radius squared. I think I should have divided this by 1/2. I didn't do that in this slide. So really, that pi should be pi over 4. So my apologies for that. My smartboard's broken, so I'm not able to go back and fix my slides right now. Kind of sucks. I'll have to figure out a better solution for that. But for the time being, this should say pi over 4. My apologies. Okay, and so to find the intersection points for this thing, again, because there's an x inside of a natural log and an x is outside, if I set f of x equal to g of x and I try solving for x, I'm going to run into trouble. So we're going to let our calculator do the heavy lifting here. We'll plug in one of these equations for y1, the other equation for y2, and then on the graphing feature we will calculate, or have the calculator calculate the intersection points. We'll grab the x values for that and use those as our beginning and end points for our interval. All right, so that is this one. Hopefully we have some more confidence understanding these volume shapes that we're calculating using integrals. And hopefully from this lesson and after trying the delta math, you'll have some more practice using your graphing calculator. Practice using the graphing feature, practice using the intersection function of the graphing feature. Yeah, and we'll go from there.